Hi everyone, I'm going to talk about flux today, and I'm going to talk about the change in flux. If I take a loop of wire, the bold line would represent the front of the loop and the dashed line would represent the back of the loop. If I put a magnet beside the loop, let's say the north pole is closer to the loop and the south pole of the magnet is farther from the loop, this magnet would create magnetic field lines such that the field lines would come out of the North Pole and they come out the North Pole and they will go into the south, outside. Outside we have the magnetic field lines. They're coming out of the North Pole and they're going into the South Pole. Whereas inside the magnetic field lines, they go from the South Pole to the North Pole. So by sending these field lines through the loop, we are creating a flux. Flux is basically a flow of magnetic field lines through the surface of the loop. Therefore, flux is defined by phi equals the magnetic field times the surface area of the loop times the cos of the angle theta. Theta is the angle between the magnetic field lines and area, vector area in this case. Vector area is always perpendicular to the surface of the loop. So this is our vector area. In this specific case, you guys see that the field lines are going to the right, area is going to the right. Therefore, the angle they make would be 0, and cos of 0 is 1, and that's when you have maximum flux in here. So these are my field lines. Now, if I take my loop like this, and if I put a magnet right below it, if I have N here and S in here, you still see that the field lines are going to be going up. Yeah, so they're coming out of N and they're going into the S. And I want to show you the area, vector area in here, and you have magnetic field in here. You guys see that in this specific case, you have 90-degree angle between B and A. So theta is 90. If theta is 90, cos theta would be 0, and therefore flux would be 0. Make sense? So what I'm going to do now, I'm going to change the flux by moving the magnet either towards the loop or by moving it away from the loop. Now let's look at a case where I move the magnet towards the loop. If this is my loop, then I have this magnet N and S in here. Let's say the magnet is moving to the right. So when you're moving the magnet to the right, as you know, still the magnetic field lines are going away from N and they're going towards S. Yeah. So it doesn't, these field lines, they don't come from the direction of the movement of the magnet. They come from which side is north, which side is south. So therefore, what happens is that when you move the magnet towards the loop, you are increasing the magnetic field in here, with the magnetic field that it is exposed to the loop. So the loop feels that there is more of the magnetic field coming towards it because you're moving the magnet towards it. And Lenz's law says that the loop wants to oppose either the increase of the field or the decrease of the field. So in this specific case, because you're moving the magnet towards the loop feels that the field is increasing. So I could say B increases, so magnetic field would increase, and then the loop does not like it. So what it's going to do, it's going to create field lines such that the magnetic field will be opposed. So the loop will create some induced magnetic field such that it will oppose the actual magnetic field because it is increasing. So to decrease it, it will create magnetic field in the opposite direction. Make sense? So if we have if B increases, that is always the case. If B increases, which means that you have moved the magnet towards the loop, then B induced will be always in the opposite direction. Will be in the opposite direction. Opposite direction. Now you know that if B induced is to the left, which is in this case, please put your thumb along B induced and try to curl your forefingers. Yeah? Having your thumb pointing towards B induced and curling your forefingers. Curling your forefingers should show the direction of the current. You see that the direction of the current here, it's going to be in front of the loop, it will be going up. So you will have I induce that is going up. Make sense? So now let's say I have the same loop. Let's say I have the same loop and I am going to move the magnet away from the loop. So this is, I still have N, I still have S, and still the magnetic field, the actual magnetic field is pointing to the right because it always goes from N to S, but the magnet is moving away from the loop. If the magnet is moving away from the loop, what happens is that actual magnetic field would decrease because you're going away from the loop. So in this case, if B decreases, then what happens is that the loop will create an induced magnetic field to oppose the decrease. So it will be in the direction of the field, because B is decreasing, the loop doesn't like it. It's going to create B induced in the same direction to increase the field. So B in will be in the same direction always. So I have my induced B to the right as well, pointing to the right. Now, put your thumb along B induced, curl your forefingers. Curling forefingers, the direction of the curling should show the direction of the induced current. Therefore, if I want to show the direction of induced current in the front of the loop, you see that it's coming down. So I induced would be coming down.